Hey everyone, Nick Diobertis here, teaching you financial modeling. Today we're going to be looking at an example of how to apply Monte Carlo simulation. And this is going to be in the context of a portfolio model where we're looking to allocate resources between two assets. This is part of our lecture series on Monte Carlo simulation. So we introduced the whole idea of what Monte Carlo simulation is and why we would want to go about it. And I mentioned that we're going to look at an example of how to do it before getting into the more formal definition of what it is that we're doing. I think it's easiest to learn this by example. So before we look at that example, let's just quickly talk about how you would actually go and run this. So Monte Carlo simulation can be applied to any model. Doesn't matter if it's in Python or Excel, but it is definitely easier to run Monte Carlo simulations in Python. If you want to do a pure Excel Monte Carlo simulation, unless you're getting some kind of add-in, then you're going to be looking at doing some kind of data table approach, which is going to be fairly complicated to work out for more than two inputs. Um, so I generally wouldn't recommend that. You can also go to VBA, but it's generally easier to just handle this with Python. Because in Python, you just do a loop over the number of iterations. Each time you draw the random inputs, you run the model, and then you collect the outputs. So it's really not more than a few lines of code to make this happen in Python. Um, so we're going to look first at the Python example of how to do this um, because it's more straightforward since ultimately we're going to run the Monte Carlo simulation in Python. So if the model is already in Python, it's very straightforward. And then when we go over to running a Monte Carlo simulation on an Excel model in a future video, then we're going to use xlwings to go back and forth between Python and Excel and have Python orchestrate the Monte Carlo simulation on the Excel model. So the problem that we're going to look at here, which is good application for Monte Carlo simulation, is an investment problem. We have $1,000 now. We need 1,050 a year from now. And we have a choice of investing in two different assets, a risk-free asset and a stock. And the risk-free asset, being that it's risk-free, it always returns the same percentage, whereas the stock, uh, the return is going to be drawn from a normal distribution um, with a 10% average and 20% standard deviation. So the question here is how much should we allocate to the risk-free and to the stock in order to maximize our chance of meeting our objective of having $1,050 in 1 year. And I intentionally set up the values of the inputs this way so that you couldn't just put 100% in the risk free. That is not going to be able to get you to the goal of $1,050. So you do have to put some amount into the stock, but how much should you put into the stock? So the way we're going to approach this is first we're going to build out the basic model to get the portfolio value for given returns. And then we're going to get that stock return from a normal distribution and rerun the model for a number of iterations and put this all together to analyze and visualize. And then because we're trying to evaluate what's the best weight, we're going to then repeat this whole process for a number of different weights into the two assets and then pick the one which has the highest probability of achieving the objective of $1,050. So let's go ahead and jump over to the Jupyter Notebook example for this. There's already a completed example on the course site that you can download and take a look at. So this is that Jupyter Notebook, and here at the beginning, it again describes the problem and our general approach for going about it. So let's go ahead and jump into the code since we've already kind of covered this. Well, quickly, I'll just talk about the math going on here. Um, so in order to get the return on the portfolio of these two assets, we take a weighted average of the returns on each of the assets. So it's the weight in the risk-free times the return in the risk-free plus the weight in the stock times the return on the stock. Um, but we can simplify this a little bit to remove one input from the model. Because we only have two assets, the weights must sum up to one. We must be 100% invested in total. And so then the weight on the risk-free is 1 minus the weight on the stock. So we can eliminate that weight on the risk-free. And we have the return on the portfolio being the risk-free times 1 minus the stock weight plus the stock return times the weight on the stock. So translating that over into Python code, we can define some variables here for the stock return, the risk-free, and the weight on the stock. And we can create this formula here, which gets us the portfolio return. So that's just taking this formula and implementing it in Python, risk-free times 1 minus the stock weight, plus the stock return times the stock weight. And with these baseline values, we get a 6.5% portfolio return. So then we can take the initial value on the portfolio and multiply it by 1 plus the portfolio return. This is a 1-year model. So we can multiply by 1 plus the portfolio return and get the ending value on the portfolio. So this is basically our entire core model here. I wanted to keep this as very simple so we can focus on the Monte Carlo simulation. So we can just put that all into a function. We want to definitely have a function that runs our core model as we go into the Monte Carlo simulation. So this is just taking that logic we worked out, getting the portfolio return, and then applying that return to the initial value on the portfolio to get the end value. And we can pass any of these as inputs. So we can say, what if the stock return was instead 20%, then we would be getting even more money. So yeah, here just trying with some other inputs. So our core model is done. We have one function that runs the core model. And you would want to have this kind of structure for any model, any Python model that you're going to go and do Monte Carlo simulations on. You want to have one function which can take the model inputs and return the outputs from your model. So we want to get into running the simulation now. And recall that the first step in the Monte Carlo simulation process is to randomly pick the values of our inputs. And so we've got to set it up so that we can randomly pick those values. So we already covered in the continuous random variable material that we can use Python's random library and random.normalvariate to pull numbers from a normal distribution. So you'll see as I've run this multiple times, I get different values according to pulling random numbers from a distribution which has a 10% mean and a 20% standard deviation. So then we can put this together with the function which runs our model to now run the model along with a random rate of return on the stock. So here, just that same logic to get the random stock return. Then I'm just printing out what that stock return is before running it through the model. So you can see each time that I run it, we get different stock returns and we get different portfolio in values as a result. And this kind of gets into the core of why we need to do a model like this. You can see that we're getting quite different portfolio values each time. and a number of them are not meeting our goal of 1,050. And so this definitely is something we need to carefully consider if we have that goal of getting $1,050 in a year. So that's how you can run one simulation at a time. Now let's run as many simulations as we want. So we basically take that same exact thing that we just did, getting the random stock return, and then running the model with that random stock return, and we just put it into a loop over the number of iterations. We set up an outputs list, we append our result to that outputs list, um, and that allows us to run the model as many times as we want, or as many simulations as we want on the model. So we can see here it's 3 simulations, we could change it to 5 and have 5 simulations there. So we'll just take that same logic and just wrap it up into a function. Of course, you know, if you're doing this in your own model, you wouldn't want to have both still sitting around. You would just convert this into that, but they're shown separately to show how you can kind of build it out. And so this is just that same logic now in a function format. So, uh, and this now runs with 1,000 iterations by default. And here we're just showing how many results there were and the first 5 results. So now this function, we are running 1,000 simulations on the model, and we could change that number of simulations to whatever we want. So, you know, this is where I mentioned that yeah, you can run the simulation and you get some results, but you really have to analyze and visualize them to get any kind of meaning out of that. So, a good first approach for the visualization is to create a histogram of the outputs. So I'm just going to make a data frame and then put those results into the data frame as the portfolio in values, and then do a histogram over those values. Um, and we can now see um, a distribution of the outputs. The outputs also themselves look normal, the portfolio in values. We can see that it's kind of centered around, uh, this is maybe somewhere around 10 and 50. And we can see some values are as low as almost down to 600, more commonly down to 800, and we're getting as high as over 1500 or over 1400, and you know, more commonly we're getting high values in the 12 to 1400 range. And you can also, the KDE is an alternative to the histogram, which basically gets at the same concept, but it just tries to kind of smooth out the curve. So another way to look at this distribution is to say, well, you know, 5% of the time we're going to get at least this value, and 95% of the time we're going to get at least this value. So we can do that with a table of the probabilities and the percentiles of the distribution. So to get there, first we can form the percentiles that we want to look at here, just doing 5% increments throughout the whole range of percentiles. And we can use the .quantile method on the data frame column in order to see that. So we just pass these percentiles, this list of the percentiles, to the quantile method, and with that we get these results saying that in 95% of cases you're going to have less than $1,231. So only in 5% of cases do you get at least $1,231. And in 5% of cases you get lower than $900. So we're already starting to get at what we want here. We can see you know, somewhere in the 40s chance of being lower than our objective, so there's a 50-something% chance of meeting our objective. But there's a more direct way to get at this probability of meeting the objective. Another note is you don't have to do this on the column. You can do it on the data frame itself, and that achieves the same thing. And then if you have your input values in the data frame as well, then you'll see percentiles of those as well. So now we're getting to the probability of achieving a certain objective, which makes a lot of sense to evaluate in this model. Our objective is to have 1,050, and we're trying to allocate to meet that objective. And so this is kind of the main output for this model. Now, in some other models, you might not have an specific objective that makes sense, in which case you don't need to do this analysis. But it's useful in cases where you have some kind of target number that you're trying to achieve and you want to evaluate the probability of achieving that. Um, so unfortunately, there's not like a direct function in pandas to do this analysis, but here's a simple one-liner which will accomplish that for you. So you can feel free to just copy paste this into your model and change out whatever output you're looking at in the data frame. But we'll break this down now so you can understand what's going on in here. So the first part going on in here is we're checking which of the values, which of our simulations met the objective that we're trying to achieve. So we can compare a column of data frame to a number or whatever else, and it will give us a column of true false, representing we did meet the objective or we didn't meet the objective. And just to see what values that's based on, um, you can see for these first 4 rows, indeed they're above 1050. We met the objective. And then we get to this fifth row, which it was below 1050, and so we did not meet the objective. So, but then we can't immediately do math with Boolean true false. So then we convert this into ones and zeros so that we can do math with it. So now this is the same thing, but we've just converted it into 1 means that we have met the objective, and 0 means we have not met the objective. So now that covers this part of the expression. And the last part is then just taking the average. So when we take the average of 1 for yes, we met the objective, 0 for no, we did not meet the objective, that gets us to the probability based on these simulation results of meeting the objective. So that'll be explained in greater detail in the next video where we formally go over everything that we're doing. But just know for now that taking the average of this 1 for we met the objective, 0 we didn't meet the objective, will get you to an estimate of the probability of meeting the objective. So now we have a few different results and analysis and visualization of the simulation. But we mentioned in our approach to this that now we're going to have to evaluate this for the different weights that we can put into the stock. So let's go ahead and wrap this up into functions so that we can easily reuse that logic across a number of different weights of the stock. So here I've created functions for all these things that we just looked at. So first, here you'll see I made a function that takes the results from the simulation and creates a data frame from them. I created a function which takes the data frame and does the histogram of the results. And as you go to start putting visualizations into functions, you should get familiar with this plt.show. Like normally when you're doing a visualization out in a cell, it doesn't matter. But when you're running it in a function, you generally want the visualization to show up as soon as you run it so that all the output can stay in order. And this plt.show is going to ensure that. So you just import matplotlib.pyplot as plt, that's the convention. Remember that matplotlib is the plotting library under the hood for pandas. And then we just put this plt.show after any spot that we're doing a plot. And this is a general practice that you should follow for any visualizations you have in functions. And then we have another function here to produce that table of the probabilities. It creates the percentile and then does quantile on the data frame with those percentiles. And we have a function which gets us the probability of the objective. And then another function which puts all of this together, all the outputs. So it takes the results, creates the data frame, it visualizes those results with the histogram, it creates the probability table, and it creates the probability of achieving the objective, and then it returns the probability table and probability of achieving the objective. Finally, one last function, which does the whole summarization of the analysis. It calls this function to get the probability table and probability objective, and the plot is already going to be shown. The histogram is going to be shown while we call this. And then we can add some other output here to kind of separate things out. So a header here to show the probability table, and then formatting the probability table, and then some space, and then a sentence about the probability of meeting the objective, and another space. So now, when I call all this, you can see now taking the results from our prior simulation. Then we can see it shows the histogram, it shows the probability table, and it shows the probability of meeting our objective all in one function call. So next we're going to get into, okay, now let's run this with the different stock weights and try to pick which is the most appropriate allocation based upon the simulation results. But before we get there, I just want to show one other thing we can do to format the output. And that's that Jupyter notebooks work by using HTML and CSS, and we can use that to our advantage. We can actually put HTML in the notebook and display it, and have whatever kind of formatting of the output that we want. So I'm showing you a little snippet here. We can use the IPython library and the display module of that library, and we can import HTML and display from there. And then when you do display HTML, then it's going to it's going to format as HTML whatever you have in there. So you can create whatever kind of output you want with HTML here. And this is not, we're not teaching HTML in this class, but just know this H2 thing, that's a level 2 header. And so you can use this function, you can just copy paste this into your own model. You can change these 2s to anything from 1 to 6 for different levels of headings. And if you just use this function, then you just now have a function which displays a header. So you can just pass whatever string that you want there, and it's going to show a header. So that's going to be useful because, I mean, you see how much output we had just from one run here. Now we're going to have a bunch of different runs, and we want to make sure we know what output corresponds to what. So now we're coming to choosing the appropriate weight. And so let's look at 10% increments in the stock weight going from 10 to 90%. And then we're just going to do a loop over those weights. We're going to use that display header functionality we just built out to separate it out to whatever weight that we're looking at. And then use our simulation function to get the results with whatever stock weight, and then display the results. And because we've wrapped everything nicely up in functions, this code ultimately becomes very simple. And that's how you can kind of build layers on layers with Python and do quite complicated things without ever having to write complicated code. So now we see we have the results for all these different weights on the stock. Um, so we can kind of look through that and see. I mean, really, the most important output here is the probability of getting the objective, but you can also get a better understanding of what's going on by looking at the other values. So when we're 10% in the stock, you can see there's not a very big range of the possible values, but we also only have a 20% chance of meeting our objective. Whereas we come all the way to 90% in the stock, and you can see we have a much larger range here in the distribution, but we do have a higher probability of meeting that objective. So then we go back to 80%, and the probability goes up, and 70% it went down a little bit, 60% it was back up. So it looks like, between and by the time we get to 40%, it's going substantially down. So we know that the proper range in the stock is going to be somewhere between 50 and 80%. And you can run this with additional simulations, maybe run it with 10,000 or 50,000 simulations instead of 1,000, and that will get you better stability in the results. But this is the main idea here of we wanted to evaluate different weights, the probability of getting the objective with each of those weights, and setting up the functions and everything in a clean way that we can repeat all this analysis for the different weights without having to repeat the code. So that's an overview of how we can apply Monte Carlo simulation in a simple model. In the other videos in this segment, we'll look at applying Monte Carlo simulation to an existing model and also applying it to an Excel model. So thanks for listening, and see you next time.